Hello again everyone, welcome back to ptet.chemistry channel. So this is a continuation of the few alternative to practical work. This is number 2 in that series of work that's associated with the year 9 mole calculations, stoichiometry as well as reacting masses. So let's get started. In this question, you have a liquid hydrocarbon. So you might not have heard of hydrocarbon a lot, but it's basically defined as a compound that contains carbons and hydrogen atoms only. So compound containing hydrogen and carbon only. Anyway, that's not the most important thing. It's just that this liquid hydrocarbon is going to combust. It's being burnt. So some students are confused between this burning in what? Burning in oxygen, which is actually a type of chemical reaction called combustion, and this is different as opposed to boiling. If I am boiling the liquid hydrocarbon, I will provide a heat at the bottom. I will be heating the liquid hydrocarbon, but here I am not heating the liquid hydrocarbon. I am simply reacting. I'm burning the hydrocarbon, and that will give me carbon dioxide and oxygen. As you know, hydrocarbon contain carbon and hydrogen. When you react with oxygen, the carbon will react with oxygen to form carbon dioxide. The hydrogen will react with oxygen to form H2O. So those are the main two products that will be delivered via this delivery tube. It will not be the liquid hydrocarbon that boil. So do not confuse between burning the hydrocarbon as well as heating the hydrocarbon to boil it. Okay, so if you heat it at the bottom here, then you'll be boiling the hydrocarbon, but here you're burning the hydrocarbon, you're reacting the hydrocarbon. That means what comes out is not the hydrocarbon, but the carbon dioxide and the H2O product. So one of the biggest hint given in this question is the gases produced. So it's more than one gas. It's actually CO2 and H2O gases. And as it passes through here, so this is ice. Ice is at 0 degrees Celsius because water turns to ice at 0 degrees Celsius. Ice turns to water at 0 degrees Celsius as well. So this thing is a gas containing carbon dioxide and water that comes in here. Carbon dioxide does not turn into carbon dioxide does not turn into solid at 0 degrees Celsius, but your H2O, which is a gas, will condense. So the H2O will condense. The H2O gas will condense, and condensation means it goes from gas to liquid, and eventually it might even freeze, but you go from gas to liquid first, and your carbon dioxide will escape as a gas, and it goes into this lime water. Lime water is used to test for carbon dioxide. Lime water is what you call saturated calcium hydroxide, formula of which you have got to know, which is calcium 2 plus and OH minus for the hydroxide. Plus 2, because the valency is 2, being a group 2 metal cation, you'll have a plus 2 charge. Hydroxide has this OH minus. Minus 1 is for the charge of the ion. When we do the cross multiply, what we're doing is lowest common multiple. We just bring down the number. And this number represent how many of that ions on the left and how many of that ions on the right. And in doing so, we can see we have 2 OH minus and not what most students do, which is this one. This thing is wrong. The blue one is wrong because this would mean 1 oxygen, 2 hydrogen. When you can count, there are 2 of this hydroxide, so 2 oxygen and 2 hydrogen, in order for the -1 and -1, -2 overall, to cancel out the +2 charge. Okay, so be very careful about this kind of formula thing. And this is alkaline or basic, and it will react with CO2, which is actually an acidic gas. So a colorless liquid is formed in the boiling tube. They want a chemical test. So a lot of you probably know that this is H2O, and you want to prove that it's water. So because they tell you it's water. So chemical test is not a physical test. So students typically, they will put down things like, yes, water boils at 100 degrees Celsius. Water turns to ice at 0 degrees Celsius. So they're thinking about physical tests, which is to do with physical properties, melting point and boiling point. This has got nothing to do with physical tests. A chemical test here is actually used. What is this thing? Anhydrous cobalt 2 chloride. So this was in the lower secondary syllabus many years ago when I was doing my lower secondary science. However, it's now been taken off that syllabus, that curriculum for lower secondary, but you will come across this again at some point in your O level or your IGCSE chemistry, where this is anhydrous because it doesn't have the water of crystallization. So anhydrous cobalt 2 chloride is blue in color. So it turns from blue to pink. So blue is the original color. It turns from blue to pink. Okay, so some people would like to use the other option. The other option is use anhydrous copper 2 sulfate, CuSO4, copper 2 sulfate is Cu2 plus, SO4 2 minus, and this will turn from anhydrous copper 2 sulfate is one of the practical on reacting masses or gravimetric analysis. You heat this blue solid which was hydrated and you get the anhydrous solid which is white in color. As you add water to it, if water is present, it will go to blue. So these are reversible reactions. They can go from anhydrous to hydrated, going from white to blue. This one is going from the anhydrous, which is blue, to pink, which is the hydrated cobalt 2 chloride. You'll learn more about this at a later stage. Now suggest why the boiling tube is placed in a beaker of ice. You already know that it's water that you're collecting. So this is to condense. The word there is to do condensation, to condense H2O gas, or you can say steam, which is the gas produced, into water, which you want to collect, which they tell you that the liquid is water. Carbon dioxide is also produced by burning the hydrocarbon. As I said, this is a combustion reaction. Complete combustion, meaning you have enough oxygen. Complete combustion of hydrocarbon will give you CO2 and H2O. What effect does carbon dioxide have on the lime water? It will turn lime water milky or cloudy. So this is a classic test for carbon dioxide gas, milky or cloudy, and you've got to be able to do this as stated in the paper 3 practical study, because you have also done this test a few months ago, when I asked you to breathe out and bubble CO2 through this saturated calcium hydroxide, which is lime water. So if you think about the chemical reaction, so this is aqueous solution because it's a saturated solution, so it's soluble. Saturated means the maximum amount that can dissolve in it. So lime water, so you have lime water that you bubble CO2 through it. So what's going to happen then is you will produce calcium carbonate plus H2O. Why is this? Why do they do that? Because this is a hydroxide, this is base, or you can call it alkali, and this is an acidic oxide. Acidic oxide meaning to say it is going to be acid, and this thing is the salt that you're going to get because this is a classic neutralization reaction. As you know, in a neutralization reaction, it's a classic one of 5 general reactions that you got to know as part of the mole equations and balancing equations, that kind of chemistry, underlying chemistry. This question is balanced as such because well, it's meant to work the way it is. This thing is a group 2 carbonate, so all group 2 carbonates. So all the group 2 carbonate is M2 plus CO3 2 minus. So MCO3 is insoluble in water. I told you as we did ionic equations a few weeks ago. If you watch back those lecture tutorials on ionic equation specifically, I told you that there's a relationship with solubility of salts. This is one of the salts. All the group 2 carbonates insoluble in water. That's why you get these coming out from the solution and the gas bubble through the solution. You get a milky, you get a cloudy, you get a white precipitate. Now this experiment is repeated, but this time with sodium hydroxide. Sodium hydroxide is Na plus OH minus. The formula is going to be NaOH, just like that. It's going to be the same thing. It's a base, it's an alkali, so it will react with CO2. As you can imagine, NaOH plus CO2, base plus acid will give you the salt. The salt now is Na plus CO3 2 minus. That's why you need 2 of the Na plus, and you will get H2O. Don't forget that you got to balance your equation. So 2 NaOH, and in doing so, I think my equation is balanced now. So happy as it is. The carbon dioxide produced by burning the hydrocarbon reacts with sodium hydroxide. This sodium hydroxide is in excess, so this thing is in excess actually, and I'll tell you a little bit why it's in excess. After the hydrocarbon has been burned, the mixture in the conical flask is now what you call Q. Q is now titrated with 1 mole per dnq HCl because Q has remaining unreacted NaOH. This is what you put in all together. Some of them reacted with CO2 as per this equation. Some of them reacted with CO2, but the thing that remains will be unreacted NaOH, and this is solution Q. And solution Q is what you do titration. Titration is this Buret pipette kind of thing, which you need an indicator to tell you. Initial, final. So you read to Buret from top to bottom, as you would have known because you have used a Buret before. For those of you who haven't had this opportunity, you really should know how to read it. Perhaps you can watch one of my experimental tutorial video to actually learn it if your school doesn't actually allow you or enable you the opportunity to conduct chemistry experiments, which in my opinion is really bad because there is almost no way to learn chemistry without being in the lab and touching all these apparatus. You should be able to come up with this table on your own as you become more and more experienced with it. Not just filling it in, but coming up with a table because you know how to use them. You should be able to come up with a table and label them, final reading, and then the unit with a stroke, and then the unit of volume. And then this is the volume. The difference between the final and the initial is the volume of this thing in the Buret. This is 1 mole per dnq HCl because that's what you fill the Buret with. Let's start reading the Buret reading. This is 0.0. As your initial reading. It has to be done to 1 decimal place. For O level or IGCSE level volume reading on the Buret is 1 decimal place. This is 24, this is 25, so this is not 25.1 because you're going downward. So this slightly longer one is 24.5, 0.6, 0.7, 0.8, 0.9, so 24.9. And then the difference onto your calculator is 24.9 as well because this minus this gives you 24.9. Initial reading 5.1, 5.2, final reading 29.1, 2, 3, 4, 5. Pop that into your calculator, you get 24.3. Initial reading 14.1, 2, and 3. Final reading, slightly longer one is 38.5. Convince yourself 1, 2, 3, 4, 5, and then 6, 7, 8. So 38.8. So what happened then is 24.5. You should use your calculator on this, by the way. As explained in ATP1 previously, your best titer that you put a tick on should be plus minus 0.2 cm3. Ideally speaking, you are not expected to always have them difference of plus minus 0.2. You want them to be as close as possible in the real titration because it's you doing it drop by drop. You should get them as close as possible. But what you do is, if this is someone else's result, you can put a tick on them for your best titer, provided they are plus minus 0.2 cm3. So here I can put a tick on these two, but not this and this because they are too far apart. These and these are too far apart because they are 0.4 cm3 apart and not within the accepted margin. This is the accepted error of margin. In the table, take the best titration results already. I need to calculate the average volume. As I mentioned in the last video, this is what you should do, not just when you're doing alternative, but also when you're doing real practical. So take the two reading, 24.3 and 24.5. Make sure you put a bracket on them because if you forget the bracket, when you key in your calculator, you will make a mistake, and that mistake can be very, very fatal. I write down my unit in my working as well because units are very important. They are my identity and they define who you are. Yes, the units are provided here, but by doing it here, that I will not make a mistake because I know it's in cm3. Now calculate the moles of HCl in the average volume of that. So using the average volume, so this kind of question always try to guide you step by step. Try to take their initiative. This is mole per dm cube. This is volume in cm cube. Number one mistake, do not forget to convert cm cube to dm cube because you know how to follow the units. The units there will be mole per dm cube. Once I divide by 1000, my unit is now dm cube per dm cube times dm cube is going to give me mole, which is what I intended to find. So the units never lie to you. In fact, it's people who lie to each other. Okay, so that one is to 3 significant figure as per this thing, 1, 2, and 3, 1, 2, and 3 significant figure. So this is my appropriate number of significant figure throughout the rest of my calculation. Use your equation, well, use the equation, and your answer to part 2. This is the mole of HCl, and this is the mole of NaOH. I have 25.0 cnk of Q, which was the solution I made up. After the reaction, I just took 25.0 cn cube out for my titration. So the mole of NaOH is to the mole of the HCl is 1:1 from the balance equation, always from the balance equation. I want the mole of NaOH in 25 cm cube, and I have the mole of HCl that reacted with that 25 cm cube that I pipette out. So this is mole, this is mole, this is mole, this is mole. So I just bring that up, and hopefully you can see the mole of NaOH in 25 cm cube is going to be that multiplied by 1, which is the exact same thing. Now calculate the mole of whatever that NaOH in 100 cm cube of Q. Remember that after your reaction with CO2, there is some NaOH that's left over, and this is 100 cm cube. So I have 100 cm cube of that leftover, which I label as Q. Then I use a pipette out 25.0 cm cube. That's the apparatus I use. And I take out 25.0 cm cube of Q. From here to here, this is from the same bottle, so the concentration is the same. The concentration is the same, and therefore, since the concentration is the same, N equal to CV, if C is the same, is constant, N is directly proportional to volume. The greater the volume, the greater is the mole. The lesser the volume, the lesser is the mole. So I can say in 25 cm cube of Q, I have 0.0244 mole of Q. Therefore, in 100 cm cube of Q, I'm going to have more. I'm going to have greater number of mole by how much? So I'm going to multiply by the bigger number divided by the smaller number. This is called ratio. This is called direct proportion. This is called mathematics in your lower secondary mathematics as well as your upper secondary mathematics. This is 1, 2, and 3 significant figure, and this thing has a unit. So I will maintain the appropriate number of significant figure, which the question doesn't tell me, but it's based on the data, which is based on the previous data, and so on and so forth. Now calculate the number of moles of NaOH in the original. Original means it's the total that you add. It's the total that you put in, not after the reaction, but the total amount you use. So this is the total mole of NaOH used, which is equal to 100 divided by 1000 to convert cm cube to dm cube, because you know better about units by now. So that thing give me 0.2 on my calculator, but you know what is appropriate number of significant figure? It's not what your calculator show you, it's what you know based on the precision of the data. 1, 2, and 3. 1, 2, and 3 sigfig. So you gotta be appropriate number of significant figure based on the data given, based on the rest of the data in your calculations. Use your answers to part 4 and 5. What is the mole of NaOH which reacted with the carbon dioxide? This is unreacted. This is unreacted NaOH. Remember what you put in, which is the total. Some of them reacts with CO2. Out of this total that you put in, 0.200, some of the NaOH reacts with CO2. Some of it reacts with CO2. But some of them is unreacted. And if you know the mole here, which is the answer in part 4, the mole of NaOH in this 100 cm cube of Q is 0.0976. This is what remains unreacted. This is what you put in. So the difference between these two is going to be whatever that has reacted with CO2. So it's going to be your answer in, well, this one minus this one. So the mole of NaOH reacted with CO2 is going to be the total that you put in minus whatever that remains, what remains unreacted. So they give me 0.1024. Now this is 1, 2, and 3 significant figure I want. So I will run it up to 0.102 mole because they're asking for mole, and this is 3 significant figure. The unit there is mole. Alright, so just because my calculator show me this, I need to make a good decision to run out my final answer to 3 significant figure. Finally, actually not the final bit yet, use the equation and your answer to 6. Calculate the moles of carbon dioxide produced. If I have the mole of these, then I can find out the mole of carbon dioxide, because the mole of carbon dioxide is to the mole of sodium hydroxide is 1:2. I wrote down this equation earlier. This is just an acid plus base, give you the salt and the water. The difference with the calcium hydroxide lime water is that you produce calcium carbonate, which is CaCO3. Here this is Na plus CO3 2 minus. That's why you need 2 of the Na plus. These are very basic and fundamental, simple year 9 chemical formula. So I label my stuff. Could be the other way around. This one is from the balance equation. Now this is the actual amount. I just need the actual amount of CO2, and this is based on the actual amount of NaOH that reacted, so 0.102. So the mole of CO2 actual, I bring that up, that's going to be half times 0.102. And I get 0.05. Ideally speaking, perhaps I should use the more accurate value for my calculation, which is 1024. So perhaps I can just say that. So 0.1024 divided by 2, I get 0.0512. 1 significant, 2 significant, 3 significant, so I am all right there. 0.0512. Appropriate number of significant figure is based on the data given. Now the next part of the question coming to an end now. So we have the mass of the hydrocarbon, we have the Mr. So the mole of the hydrocarbon is going to be mass of Mr. So whatever you do, do not try and just write all over the place. Try to keep a certain standard, to account for any mistakes and this kind of thing. Careful, that is not the answer shown on my calculator. The calculator just showed 8.48837 blah 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 blah. There is a times 10 to the minus 3. I want 3 significant figure only, so I need to add 1 there because this is greater than 5. So this is 8.49 times 10 to the minus 3 mole. So this is 3 significant figure. I need to make clear of that very, very clearly. Okay, so gotta put them in. 8.49 times 10 to the minus 3. These are called standard form. I have no hesitations at all to put this down because this is just what my calculator showed me, because I know any day, anytime I can press this onto my calculator. Unfortunately, if you don't know how to press it onto your calculator, you gotta ask. You gotta ask now instead of having to wait later when you might not have the chance to do it all over again. In this last question, we are told that the general formula of alkane, where N is a whole number, CnH2n plus 2. Use your answer to part 7 and part 8. Part 8 is just this one. Part 7 is 0.0512 mole of carbon dioxide. This is the mole of carbon dioxide, 0.0512. So the mole of CO2 is 0.0512. You can imagine that CnH2n plus 2 will give you CO2, and there will be n number of CO2. So if I have the mole of CO2 is to the mole of C2H2n plus 2, which is the hydrocarbon alkane, I will have n number divided by 1. It so happened that they've used n not just as the mole, but to represent the number of carbon there. So this is from the balance equation, n number of CO2 from one of these. And your answer to part 7 is this mole of CO2. So that is mole of CO2, so that goes up there. Your answer for the mole of the hydrocarbon, which is 8.49 times 10 to the minus 3, goes down there. So I hope you're not confused between this algebraic expression n as well as n bracket something represent mole. That's why you see all my working, I always not just label n, I always label, well, apart from this, I guess, I try to label n bracket something because it's important that we are not confused by our own action. So what do we get here? N equal to 6.03 something something something. Here you do not want it to trace significant figure because these are whole number. Just like water crystallization, these are number of carbon. They are not to trace significant figure unless they are whole number. So this is nearest whole number. So some of these come down to experience as well as sensibility, what is sensible and what is not sensible. And that's the end of the 16 marks question on this alternative to practical, which involve a little bit of combustion chemistry as well as the associated acid-base neutralization reaction. Yeah, I mean, that's it really. Okay, so if you enjoyed this tutorial video, please make sure you click the button on the bottom right to subscribe to the channel and follow me at ptet.chemistry. That is at ptet.chemistry on Facebook, Instagram, and Twitter. And don't forget to share the channel widely with all your friends, chat group, juniors, seniors, relative, and whoever else might find this tutorial video useful. Thank you for watching.